Hello everyone, welcome back to the post-lunch session. For the first talk, we have Alok continuing with his second lecture in the 3-lecture series on localization of information in quantum gravity. Over to you.
Thank you. So let me just first lay out the plan for today's lecture. So we will sort of start where we left off, except that Tom really helped me with filling some gaps. The first thing that I want to discuss, which is probably one of the most important part of this discussion, is split property in quantum field theories. And let me just be explicit without gravity. I am just being explicit here because, as we will try to discuss, at least that the split property should be something that we expect to be true even in a globally hyperbolic spacetime, not only in Minkowski spacetime. And then after this, we will kind of switch gears drastically and just go to observables in classical gravity without quantum. Because as we saw in the last lecture, that the whole program of algebraic, this formulation of quantum field theory started with an algebra of observables, self-adjoint observables. So if you want to sort of understand, recast quantum gravity in this formulation, then it's better to first have a handle on what the gauge invariant quantities are. So, and this is related to, as you will see, I will just put it in quotes, split property in classical gravity. And I think I won't go beyond this today, but of course, eventually the idea is to then look at perturbative quantum gravity. And is there any way to localize information in? So as you will see, we discussed very briefly last time, but the split property is really about localization of information in quantum field theory, as we will discuss. So this split property is at the heart of this discussion, and it's not when we switch on gravity, even at perturbative level, it becomes a controversial topic. And actually, as we will see, even in classical gravity, it's not really a completely settled issue in the sense of, because it's not completely settled what are the good set of observables in classical gravity. And I should mention that there are bigger experts in this subject in the audience, especially from Okinawa, who are doing work related to this thing, and they had a poster yesterday also. So maybe there are some difficult questions they will answer. I will give references as we go along also. Okay, so let me just start with a very quick review of what we did last time, just to connect also with what Tom discussed. So we started with the algebra AM of which was please ask if something is not clear. I will not rewrite all the details. So this was the algebra which was of unbounded operators and with no Hilbert space or anything. And then from here, as we discussed, we could define where M is a Minkowski space. So just for definiteness, we were looking at Minkowski space. And then from here, we deduced that by looking at the free field theory example, we saw that we could really think of this algebra as built out of, formally as built out of local algebras, again of unbounded self-adjoint operators. So local or maybe quasi-local algebras. Not von Neumann or anything, just abstract algebras, which satisfy causality, or actually Einstein causality, and covariance And then from here we saw that to quantize this abstract algebra, we could do the GNS construction, which for our purpose only meant that it was basically about if you take any polynomial or monomial in these abstract objects, and for all such polynomials in the algebra, in AM, if you give me values of all of these for all functions and for all n, that is basically the quantization, because we are giving all possible correlation functions. So yeah, yeah. Yeah, GNS can be done, because GNS as GNS, there is a slight subtlety, like GNS in principle works for star algebras. As a construction, GNS also works for star algebras, except that you have to look at the domain of the operator is not the full GNS Hilbert space. It's just some dense domain in the Hilbert space. Just to say a bit more, we could do it in the following way. We could look at a C-star algebra built out of these things. We could look at the C-star algebra, and then we could look at GNS on C-star algebra, and these unbounded operators are derivations of the C-star algebra, and then so there is a direct connection with the but I just didn't want to get into the, yeah. Well, maybe unbounded operators is really a abstract thing. This is just an algebra of elements. So algebra closes because, I mean, the whole algebra is generated by, these are some symbols, right? So you look at multiplications and addition of all these symbols, which are parameterized, as we saw last time, with fields of smooth functions of compact support. And that's the algebra, that's it, like, yeah. So, yeah. Okay. And I think as Nima is mentioning that, maybe I will comment a little bit on this. Yeah.
Sorry,
No. Yeah.
Well, how does star algebra state? I can define the C star algebra immediately.
Yeah.
Is that the construction?
No. If I have a the construction in this case is slightly different, in the sense that I start with you could start with a star algebra, no state, just star algebra, and then you can look at all possible. You could generate from it a C-star algebra, just at the level of algebra. It's just algebra. So let me give an example. So Nima is asking the following question. Let's look at quantum mechanics. And I'm going to start with of a point particle. Yeah, actually, this is a very important question, but I will be a little brief here. So let's start with the algebra, which is the following abstract algebra. So it's the algebra which is defined by two elements, generated by two elements. So this is a completely abstract algebra. And I think most of you would recognize this is the Weil-Heisenberg algebra. And then I could define an algebra of star algebra of unbounded operators by declaring that d by d lambda of u lambda as an abstract element at lambda equal to 0. I just call it some q. And yeah, and d by d mu of v mu is defined. This is a definition of this. So q and p is the star algebra, and so the point is that in quantum mechanics we know that we could do a GNS construction on the Weil-Heisenberg algebra, and that would give us the usual Schrodinger representation of on the star algebra. Quantum field theory situation is a little subtle. So here already at the level of algebra, so this is Nima's question was extremely important in this case, that we found without any state at the level of algebra we have a connection between Weil-Heisenberg algebra and algebra of q and p, because q and p is defined like this as like a derivative of u at this lambda equal to 0. That doesn't exist if I started with this abstract algebra, or I started with an algebra of operators of this type, for example, generated by elements of this type. So again, these are elements, just abstract elements. So I could turn this into a C-star algebra by basically saying that I only look at finite linear combinations of, so each of this element, let me call this element like f. So I could look at some products of f, where each f is like this kind of an element. I could complete this in a C-star norm. So that gives me a C-star algebra. This algebra at abstract level has no direct connection with the algebra of unbounded operators in quantum field theory. Yeah. Okay, so sorry, this was a little bit of an aside, but let me just say that where we stopped last time. So then I will go back to exactly what Nima was touching upon. So so this gave us the quantization of our algebra, and then we saw that if you, for example, take omega to be translation invariant, then we had the Riesz-Leader property, and the Riesz-Leader property I will just rewrite again. Maybe I will erase this. So again, at this point, no von Neumann so far. It's just Weitmann functions. I mean, this is really giving us the Weitmann function. So just to be absolutely clear, you can think of this as just the vacuum expectation value of this operator, just to be completely connect with the usual QFT literature. And then as yeah, function f is supported as M, and we saw that this algebra can be obtained in terms of these local algebras, and these local algebras satisfy some condition which were motivated by the free field example for us. So they satisfied this condition that if O is in O prime, O is in O1, then AO is a subalgebra of AO1, and there was this Einstein causality, right? And there was a relativistic covariance. So the Riesz-Leader property, I will just summarize again. So but please ask if I'm saying some rubbish. So the Riesz-Leader property basically says that if omega is translation invariant, by which we mean that if I take omega and I apply some translation, say alpha t1, alpha t some spacetime vector. Okay, let me call it a1 phi f1 alpha a1 phi f2, same a1, then that is same as omega phi f1 phi f2. Or if you have a free field, then of course, or if you have a state, as we discussed, which is a quasi-free GNS state, then you just have to check this for a 2-point function, but in general, of course, for any n-point function. So if omega satisfies this property, then as we saw that a omega acting on the state in the Hilbert space corresponding to this, which we call omega, is is dense in whatever the Hilbert space we find via GNS construction. So all the states in our quantum field theory, almost all the states are constructed by just looking at one of these for NU. So this was the Riesz-Leader property, which physically is just telling us that there's always entanglement in quantum field theory. And this was really proved only for, the way we formulated, of course, it was only for Minkowski spacetime, because as we briefly discussed, this condition came out of the spectrum condition, which of course relies on translation invariance. I should mention that there is a lot of work in algebraic quantum field theory is about generalizing the so-called spectrum condition, and it goes under the name of micro-local spectrum condition. I don't have time, but if in the end there is some question, we can discuss it. It's one of the major results of what it means to have a positive definite Hamiltonian even in a curved space-time, and it's a big success in the algebraic quantum field theory. But we will not discuss it directly. So anyway, so this one relied on the spectrum condition. Okay, and now just to connect. Oh, it's just phi of alpha inverse on f, right? It's just translation. So you can just apply a translation on a function. Yeah. So this is a under this condition that if you give me the if your vacuum basically is translation invariant, then you to generate almost the full Hilbert space, you have to.
This is the Riesz-Leader statement in this language, right?
Yeah, this is the Riesz-Leader statement which assumes that the omega that we started with, which in our language was basically this, that is translation invariant. That's what. So this is just the usual Riesz-Leader. Nima, is that okay? Yeah, that's the usual reach leader. And now let me just connect with what Tom said in the. So how do we go from here to one-Newman algebra? I will, because he already covered it, so I will just be brief. But you please stop me. Yeah. No, here it was space-time translation invariance, right? That's a very good point. So I think even if you have thermal state, but maybe Nima can know more, which has only spatial maybe translation invariance, I think there is some reach leader that you can prove. Yeah, it's important here. It's important. Yeah, because causality was important here in the proof. Yeah, but so even for thermal states, there is causality, of course. I think. Yeah. The argument I gave really relied on we having anyway relativistic translation invariance, because we saw that the unitary representation of the translation group had a support only in the forward light cone of the momentum, right, last time. So that clearly was very relativistic statement. Which one? Yeah. So for our purpose, for this discussion, just really think of this as, if you give me for all elements of your algebra, it's exactly same as giving that there is a vacuum state. So you can just think of this omega giving us a vacuum which is cyclic, and as Tom said, separating. It generates all states in the Hilbert space. So think of this as in a one-to-one correspondence with this. So this is equal to this. No. That's no. I mean, that's the whole point, that the states take a secondary role in algebraic quantum field theory. So in principle, you don't. In principle, the formulation of algebraic quantum field theory does not rely on isometry. If you have isometries, then you should have this covariance condition on your algebras. But in principle, you may not have any isometry for the algebras. You will still have causality, but there may be no isometry. No, this I don't. No. This I don't know. There is reach leader for Visitor, for example, that has been proved for free fields. I don't, to my knowledge, I don't know if the reach leader has been proved in general. Although the spectrum condition has been generalized to any globally hyperbolic spacetime, but it's really something that will take us far from what we want to do. So I am not. It's one of the celebrated results in algebraic quantum field theory, but unfortunately we don't have time to. So if you Google this name, then you will see lots of papers talking about spectrum conditions. So, yeah. Okay.
Correlation functions are basically Poincare invariant, then we get intense states of the Hilbert space using the algebra on the bracket.
Yeah. Well, we just have to look at local algebra. We don't have to look at full AM. Take any O, our causally convex open set, and look at AO as we discussed. That's enough to generate all states in the almost. I mean, what is called dense subspace in the Hilbert space. That's reach leader. Yeah.
Yeah, I'm somehow confused about a trivial point. That imagine that you have a scalar field theory with no kinetic term, just a mass term, right? M square phi square, auxiliary field. So all the delta Green's functions are just delta functions.
Yeah.
Right. So does this satisfy the reach leader theorem? Because here there should be no entanglement, right?
Yeah. I don't think it will. I mean, I think that
but it is
because we require the No, I don't think it will, because at the end, this, for example, of a free field, the 2-point function will be given in terms of the causal Green's function, right?
Delta function. Right?
I mean, so that I think that we are ruling. So remember, we started with the star algebra, and the star algebra had the commutation relation, which had the retarded minus advanced Green's function, and we are assuming it's they are causal propagating, like not static delta function Green's function. I don't know what happened. I have not checked, but I would.
I mean, this is still causal, right? It's just a very special.
Yeah, it's very special. I agree, but it's like singular to singular. I would have thought.
I see.
So, but I don't have a good answer.
But weird Green's functions probably still exist in this.
Yeah, but maybe it is. Yeah, I don't know if Nima knows. I mean, I think we can't define algebra with that, but I'm a bit. I have not checked this. Yeah.
I mean, if you want propagation, like time evolution in that theory,
Yeah.
I think
Yeah, no, Ashok is just saying his theory is just m square phi square, right? Like that's it.
Yeah,
He has nothing else.
Yeah.
So it has no time evolution.
It has no time evolution. So it's one of these. I don't know.
Time evolution is trivial, I guess.
Yeah, it's trivial.
Yeah, well, maybe not. Yeah.
It's like this one of these infinite boosted Carolean type theories or something, is it? Which
Maybe.
kind of remain on one. Yeah, but they are effectively Euclidean. So I don't know. They become effectively Euclidean, no? Or,
No, I define it as in Lorentzian space.
okay, but yeah, so I don't know. Okay, I should. I think none of this would work in the sense that even for me the algebra itself I started with which had dynamics.
I see.
So, yeah, but we should we should think about this.
Thanks.
Okay, so if there are no other questions, let me just quickly run a thing from how to connect what we are doing with what Tom was doing. So this is absolutely related to what Nima just mentioned. So so far we have looked at, so we have started with these AOs, and then we have given some representation. So let's indicate it like this. So now we have these operators. These are abstract elements in the algebra. These are some operators which act on the Hilbert space H. Some Hilbert space which has a cyclic and separating vector corresponding to omega. And the connection of this unbounded stuff with what Tom talked about briefly is the following, that you can look at, instead of this exactly as Nima mentioned, we could look at, let me just call it representation of bounded operators, which Tom also mentioned briefly. So think of, as he said, that you consider out of the unbounded operators, consider all bounded functions. You just create all bounded functions and look at representation of all of them. And so now in this algebra, so let's just call this, let me just look at this one, and let's look at its double commutant. And let me just call it m omega. So in general, what happens that this algebra constructed out of all bounded operators, it is what is called a C star algebra. It's not intuitively, it's just algebra of bounded operators if you want. It's it has more structure than that, but let's just, for physics purpose, our purpose, just think of bounded operators. And so now the point is that if you take this guy, and if you can ask, why is this not a von Neumann algebra? I think Tom explained briefly. It's not, because we know that if I look at the commutant of, if you look at the commutant of this operator, oops, sorry, then that is contained in the they are not equal. I mean, that's it's just contained in the algebra of the causal complement. But if I look at this one, then you just have to notice the following thing about a bounded operator. So there's a small lemma that you can immediately check. It's very simple to prove, which is that if you have a, let's say that S is some subalgebra in the algebra of bounded operators, then S, the double commutant is always a subalgebra of S, but the triple commutant is equal to S prime. But this is simply like a definition chasing. You can immediately check this. And because of this, what happens is that if I look at m omega O commutant, double commutant, sorry, you can check because of this lemma that this is same as m omega O for all O. And so that is how we end up with von Neumann algebra. So this is really what Tom was talking about, von Neumann algebra of QFT, of local operators. Okay, this was a bit quick. So if there's a question, just so that you know that what I'm trying to discuss and what Tom was discussing are not different things. They're just absolutely related. Yeah. Oh, sorry. Yeah. What did I write? Thank you. Yeah. So is there any question so far? Otherwise, we can now go to the split property, because to discuss split property, we have to go to the world of von Neumann algebras. That's why we need this. We cannot discuss it at the level of, for many technical reasons, simply because the theory of C star algebra is not developed to that extent. So we can't discuss what we want to discuss about preparing states locally in the world of C-star algebras. That's why we kind of forced to go to the world of one-Neumann algebras. Yeah, everywhere. I mean, so already this. So we are defining. I was trying to tell you where. Remember, one-Neumann algebra is a subalgebra of bounded operators on the Hilbert space, right? So that is just the definition of one-Neumann algebra. I was trying to tell you how we get this from what we started with, which started with some abstract algebra, which really correspond to basically polynomials of field operators. So it's unbounded, and then from there we constructed representation, and then we can look at representation of the bounded operators. That's not a one-Neumann algebra. But if given any O, if you look at the double commutant, then and you look at this and look at look at the algebra generated by this thing, that is a one-Neumann algebra simply because of this property. So this is just just connected with what Tom was doing. But now once we have this, then we can ask many questions. What type of one-Neumann algebra this is, and what can we prepare a state in a lab without affecting the state in some other faraway galaxy? So which is the split property. So so there are two questions that we can briefly discuss now. What type of we get in QFT, and second question is can we separately prepare states? Can we prepare states in a lab without affecting the environment, without affecting, okay, maybe its causal complement? Of course, and these two questions are directly related to each other. So let's try to understand the answer to both these questions. So I will, because Tom discussed already the different types of algebras, I will just take his definitions. But of the type 1, type 2, and type 3 one-Neumann algebras. And let's just first look at the following thing. Sorry, I should have said that MO, this one-Neumann algebra generated MO for any O is a factor. And the reason it is a factor is because of the fact that if I look at the intersection of MO with MO commutant, then if I remember, Tom discussed briefly that there is a Haack duality. So let's just assume Haack duality, which tells us that this is same as MO intersection MO complement of O, causal complement of O. And we know that the only common elements between them is identity. And so that tells us that this MO is a factor. And let me just quickly say that this, because of causality and relativistic covariance, this MO is a type 3 factor. No, because remember our O's are open sets. That was the reason. Remember, we always start with our O's. I think that there are more elaborate constructions, but our O's were causally convex open sets. Go means MO is defined on an open set. So MO is not. You want to take some limit or something, or like O is not closed. Yeah. Right. So you have just open sets. Every MO is defined in an open set. Like once you chart, you fix a chart. Is that correct? Yeah, okay. So once you fix the chart, then inside each open set, you have operators, but there is no issue with defining on the boundary of the closure of that open set. At least at the level that I know. I mean, there may be more.
But since this is symmetric in O and O prime, and O prime is a closed set if O is open, so shouldn't this be true for open and closed sets?
No, sorry, I should have been more elaborate. It's a causal complement, which is the open causal complement. Like you just look at the open part of it. All the M's are defined on open sets. Yeah, I should have said it. Yeah, I was just being a bit schematic there. This I don't remember, I'm far from expert in algebraic quantum field theory. Maybe Nima knows, but I don't know. So if there can we prove factor without the Hug duality? There is a factor. Okay, I see. Okay. So we already have a vacuum because this is all now at the level of representation of the algebra. But so sorry, you're saying that this there could be a more. We didn't have to use this step maybe to prove it's a factor. Exactly. Yeah. So okay, at least at the level at 0th level of AQFT, maybe it's okay. I mean, yeah. Okay. So now let me first state what the split property is, and then we try to understand why. First, let me say what type of algebra it is. So, so to answer to question 1, let me just first state it, and then we try to understand it intuitively at least that that MO is type 3 factor. By which we mean that, as I think Tom introduced, for all O. By which we simply mean that any projection operator, any projection inside MO, any projection P inside MO is always of the form P tilde star with where P tilde is a isometry as he discussed, P tilde star, P tilde equal to 1. Intuitively what this means, I think, at least for non-experts like me, one way to understand this is to contrast it with the type 1. So type 1 is much more easy to understand, and so let me first recall from also Tom's lecture what type 1 algebra definition is, because that makes it clear what this type 3 abstractly stands for, and then we will give some arguments as to what this exactly means in physics terms. So type 1 algebra basically says that if you have some, let's say you have some subalgebra of bounded operators, then S is type, and let's say S is one Newman factor. Then S is type 1 if there is a unitary from H to some H1 tensored H2 such that, sorry, I have to go this side. Such that U inverse is so for all A in S. So it's literally telling us that we can always separate our Hilbert space into 2 factorized Hilbert spaces, and if all the elements of the algebra act on only one of the Hilbert spaces, for example H1, then that is the type 1 algebra. Okay, so so this is type 1. In other words, it has very simple projections because you could just, because it acts trivially on the second Hilbert space. So like all elements of the second Hilbert space give you like trivial projections for the type 1 algebra. So type 1 is this, which is really the algebra in quantum mechanics, in the sense that if you give me some spin systems which are spatially separated, and you have some, so some algebra of operators here, let's call it A1 and A2 in quantum mechanics. Then of course we know that this A1 will act on a Hilbert space, which is A1 will act on a Hilbert space from, because they are spatially separated, which it will act on a Hilbert space which is localized in region 1, for example. So if you take some local operator, then it will only excite states in this region in quantum mechanics. So the algebras, all the algebras in quantum mechanics are type 1 algebras, because it's just we can just separate states spatially, right? And there is no problem. But the issue and this argument, very nice. So the statement is why this cannot be done in quantum field theory. That's really the question. And I think the simplest answer I know of is by Young-Wasson. So there is a beautiful review. I think many of you would have seen it. It's called Role of Type 3 Factors in QFT. So I will just give an argument that he gives to motivate why the algebras in quantum field theories, relativistic quantum field theories, cannot be type 1. But I should mention that this is this is not an observation. This is a proof. The fact that a algebra is not is a type 3 is actually a proof, and proof. So let me just give a brief history of this this development also. So it was way back when this Haag-Kastler axioms came. Araki showed that for a free massive scalar field, algebra of local operators cannot be type 1. So he has a paper, it's a small paper, 4 or 5 page, where he shows that MO has to be either type 2 or type 3. He cannot convincingly prove it's type 3, but he convincingly showed it's not type 1. And then in 80s, Friedenhagen had a paper where, Buchloz had a paper which was considered to be the first development. So maybe I should write it here. So let me just write at least a brief history of how this type 3 thing was realized in EQFT. So Araki was the first one to observe that it's not type 1 algebras in QFT algebras. And then the first important paper came by who showed that for in a free field theory, for a massive free field theory, it is type 3. In quasi-free states. I think this was in around 85, and then after that there were many other developments, including by Friedenhagen, Longo, and others. And I think by now it's taken to be more of a I guess I don't know, axiom or just a result that in relativistic quantum field theories these local algebras will always generate a type 3 von Neumann factor. Okay, let me now give you this intuitive argument that Young-Wasson gives as to why it cannot be type 1 at least. So it's kind of along Araki's line, that why it can't be type 1. He gives the argument in a much more precise way. I'm going to give a very souped down version of his argument. So his argument is the following: that suppose you have, suppose let's say the following could be true. The way we think that there is an atom. There is a localized system, that's like atom 1, and then there is atom 2. And suppose we could say that, okay, as we would assume that there are some wave packets we could prepare which are separated. So there is some Hilbert space for atom 1, and there is a Hilbert space for atom 2. And let's say that, so suppose this is true. So the argument is by contradiction. Suppose this was true. And so let's say the atom 1 is in the ground state. Oh, sorry, atom 1 is, let's say, in the excited state. And atom 2 is in the ground state. And we prepare the system at t equal to 0 in some frame. But then we can ask the question, okay, what is the probability that at time t, so what is the probability that at time t, atom 2 will not be in the ground state? So that suppose we ask this question, and let's say that the spatial separation between these two in our frame is, say, L. Then of course you notice that for all t less than I'm of course using c equal to 1. For all t less than L, this probability will be 0. But for all t greater than or equal to L, it won't be 0. But then you can use the spectrum condition, the fact that the Hamiltonian is bounded from below, to show that PT has to be analytic in the upper half plane. In the complex T upper half plane, PT has to be analytic. And that kind of tells you that this cannot happen, that suddenly PT cannot switch from 0 to non-zero. Is this at least the paradox clear? So that basically tells us that something must have gone wrong in our setup, and that what went wrong is the fact that we assumed that we could have a factorized Hilbert space like this. Yeah, I mean, you can do an analysis, the fact that your energy is bounded from below, to show that PT is analytic in the upper half plane. Right? Just causality, right? It's basically just causality. And then you use edge of the wedge theorem to argue this cannot happen. It cannot be 0 for some segment of t and then not 0 for other times. And so basically that means something must have gone wrong, and this must have gone, this must have gone wrong. Right? So, or at the level of algebra, I should have really said, like, this must have gone wrong, because we assumed that we have some factorized algebra A1, A2. This is very schematic argument, but at least I hope it shows that the key point was relativity, of course, because you have causal propagation. And that gives rise to this paradox. And then he goes on to elaborate this paradox and shows that, gives very convincing argument, which is now then a detailed analysis, that it should be type 3. This argument is not telling us it's type 3, it's simply telling us it's not type 1, even at the level of crudeness of this argument. But, so I encourage you to look at this beautiful review. Huh? The paradox is by Fermi. Yeah, I should have said that. Sorry, yeah. No, the paradox is by Fermi. I don't think Fermi was doing algebraic quantum field theory, but yeah.
Higginfield claimed that even at arbitrarily small times, the second atom can be in an excited state. So,
yeah, which is related, I guess, to the statement, right? That
so was this
exactly
wrong?
No. So that's what I'm saying. That I mean, then it will be a detailed discussion. Basically, now this probabilities for individual states systems will not make any sense anymore, because our assumption was we could define probabilities for like this system separately from this one, but I think you show that you have to you have to define only conditional probabilities. So okay, so that basically, I hope that gives at least some idea why it's not type why it's not type 1.
Alok, what was the initial state that you prepared?
Yeah, well, the initial state was one atom was in excited state, some excited state, and one in ground state. I mean, you assume there is a factorization first, and then you assume that, okay, you are in some highly excited, some excited state and some ground state.
Atom 2 was in the ground state.
Yeah, and then you say, okay, so there is a finite probability that this will relax, emit, and excite the other one, right? So he has a much more detailed analysis, I must say. I'm really not doing justice to his argument. Okay, so that now that's the issue that so that what that tells us is that we cannot write. So let me just give the outcome of what this analysis is telling us, because that's most important for us and for later than the split property. So what is this thing telling us? What is this telling us? That MO is a type 3 factor. it is really exactly telling us, sorry, for all O, it's exactly telling us that there is no unitary which we can find, which can split H into some H1 tensor H2. There exists no unitary like this, such that U MO U inverse is in so this is really the I would say the immediate physical outcome of saying it's a type 3 factor, that we could never separately think of a Hilbert space. We could never factorize our Hilbert space into a localized Hilbert space and another one, such that this MO only acts on the localized Hilbert space and nowhere else. So there doesn't exist any such unitary. And
look, I have a simple question. I mean, these two systems are, I mean, if you try to write down a Hamiltonian for these systems, then they are interacting with the electromagnetic field, right?
Exactly. So actually, that's an excellent question. So actually, if you look at his proof, you are right. He has 3 algebras, A1, A2, and the radiation field algebra. And really, to really analyze these things, you have to look at that. But at the level of this argument, I just didn't include it. I really, again, I should say that I feel kind of bad that I'm doing injustice to his argument, which is quite much more robust than what I'm giving here. Yeah, because you want the time taken. I mean, you just want this statement to be true that, okay, sorry, by the way, this is Fermi's original paradox, right? So he just started with the Fermi's paradox, which is really the fact that radiation field is massless. And you want to understand why what is the resolution of the paradox? And the resolution is that we assume that the algebras are factorizable in local regions, but they are not factorizable. Yeah, this is Fermi's setup. Yeah, you have some atomic systems and you have radiation field also. Yeah, so you have, exactly. Yeah.
Put the whole system on the lattice, including the electromagnetic field, right?
Yeah.
Everything would be tensor products.
That's type 1 infinity, what we would call type 1 infinity, for example.
But you would have a notion of causality. You don't lose the notion of causality.
Yeah. So no, I'm not disputing. I agree completely. But remember, the whole thing was to do continuum quantum field theory.
I know it's an aside, but
yeah.
I could still phrase this story on the lattice.
Yeah.
Because it's at root is
absolutely. Yeah. No.
At least there would be all tensor products.
Yeah. Yeah, you will have. I mean, also, yeah. But your relativistic covariance is broken. At least we softly broken. No, your lattice. You have a lattice. Yeah.
There would be no effect.
Yeah.
And then there would be
They would immediately be.
Yeah. Right. Lattice size, yeah. Right. Okay. But it's correct that it will just be type 1, right? At that level, it just be type 1. So, but I mean, of course, philosophy of quantum field theory is that the continuum quantum field theory is, if you want to study it, we should study it continuum and not on lattice. Like that. That is their, at least as far as I understand, that's their philosophy. Yeah. Okay. So now in this light of this, then it looks a little bit hopeless that this seems like telling us that we cannot. If this is not true, it looks like we cannot prepare states locally in O, because there is no way that O will only act on some Hilbert space localized somewhere and not anywhere else. And this is where split property enters. So let me, with this subtlety, with this constraint thrown on us by type 3 structure of the local algebras, I will state split property now, which saves us from this disaster, which basically tells us that we can prepare local states. And as I will discuss, the direct corollary of this is localization of information in QFT. I will come to in a minute after discussing this. I haven't defined this notion yet, but I will try to define it after we discuss split property. So let me just first state what the split property is. I think, sorry, I should mention one more thing. I forgot to mention that there are other results. In fact, sorry, I should have said. So this Buchholz mail, I'm just going a little bit back. Buchholz proof of type 3 nature of type 3 ness of MO. It relies on everything we have discussed so far, and another. So his proof assumed more. Of course, the proof has later been developed by relaxing this assumption, but his proof also assumed that the omega that we started with is, and I will explain what I mean by this, sufficiently well behaved in the UV, or what is often called, it satisfies Hadamard condition. So I will just now write what this condition is. So this was an assumption on omega in Buchholz's original proof, and basically the statement is the following: that if you consider our omega phi f1 to phi fn, now you do the following thing. So this, as all this, let's say all these f1s to fn, let us say that all of them are defined inside a single O, for example, because of course we are looking at MO. So we are looking at correlation functions of localized operators inside MO. And so now, like as someone was asking before also, let's go to the boundary of this. So we have a, this is O bar, let's say, for example, this thing is O bar and the interior is O. And the statement, the assumption was that omega is sufficiently well behaved when you go towards the boundary of O, in the sense that if you do a following scaling operation, so you consider I will explain what this notation is, where fi lambda on x is fi x by lambda, then there is always some positive function of lambda, let's call it f, positive and monotonic function of lambda to the power m, such that this limit is finite. And for quasi-free states, this condition is precisely the Hadamard condition on the short distance limit of the 2-point function. So maybe this is relevant for people who look at the black hole horizon, and so for example, Boulevard vacuum won't satisfy this condition. So this was assumption. I just wanted to say it's an important technicality, and it has led to some important results even in recent times, in the sense that maybe I'm slightly digressing, but let me say this. So recently, a group of people came up with some supposedly localized states inside these light-like regions. They are called Sorkin-Johnston states. And they were not using AQ of T or anything. They just said that, look, using some causality property, I can define states which are localized inside any finite region. And it was later proved by algebraic quantum field theory people that they precisely violate this regularity condition. And so that is why, these new states were not a counterexample to the type 3 nature of the quantum field theory. And so I think they are now no longer considered. They are quite ill-behaved at these corners, like the Boulevard vacuum, for example. So in the black hole case. So no, the completion, the closed completion of O. Yeah. Okay, sorry. So now let me just state the split property. So I'll pictorially just show the split property. Again, this discussion on split properties, let me first give the reference. There is this review that I mentioned, Kasya, and I think 2016, and there is a very nice sort of reviews plus original result by Fuster, I think in 2015, which the title is Split Property in Flat and Curved Spacetime. So the first section of this is a very good review of the split developments of the split property, like the results split property. So the idea is simply the following. Let's suppose this is my suppose this is my say O1 and this is my O2, O2, and these are both type so MO1 is type 3, and of course MO2 is also type 3. But we can do the following. We can consider sandwiching O1 inside a slightly larger region. Again, a causally convex open set, so let's call it O1 tilde. And the statement of Buchholz at least was that if the state that we started with omega is sufficiently well behaved, which was that condition that we wrote there, then MO1 and MO1 tilde were sandwiched by type 1 algebra. So of course MO1 tilde is also type 3 because that's a causally convex open set. But if the omega that we are defining is such that if you consider like take the correlation function here and take limit at the corners, it's sufficiently well behaved in the sense that the singularities are like Hadamard, then we can always do this kind of inclusion where this is so I will explain what this is where this is type 1. Oh, I already wrote that, sorry. Yeah. So now let me try to quantify this a little bit, but this is the statement. And so this statement is very, very useful because then it is telling us that I could really I could separate I could prepare states in O1 because I could always think of preparing states in N, and they will not affect what is happening in O2. Okay, that's the basic statement. So let me try to first explain what this is and then why it implies that things get split nicely. So is there any question about at least the statement? Yeah. So the statement is that if my goal is the following, I want to be able to see if I can prepare a state in O1 without affecting the states in O2. Yeah, that's my goal. Oh, sorry, I should maybe let me. These are space-like separated, of course, causally separated, causally disconnected. And so right now we are that is our goal, whether we can do this or not. And for the statement right now we are saying is that okay, first think of O1 inside a slightly larger region O1 tilde. And if your omega satisfies these regularity conditions, then already between the MO1, which is type 3, can be included in a subalgebra in N. Okay. Now once you have N, which is just type 1, so type 1 means it only acts on states locally, as we will see, and not affect anything else. That means I can prepare state clearly in O1 because N is N is sort of related to N includes the algebra N includes MO1. So I can prepare states in O1 without affecting anything in O2. Okay, that's the physics of split property. No, actually, that's a very good point. So the proof itself, but yeah, I mean, yeah, that's a very good point. I mean, it's a technical thing, it just comes in this. Even when I knew this proof, I didn't understand most of the details. Now I've even forgotten, so I remember even less. But yeah, I mean, it's, I don't know, maybe Nima knows or Tom knows where we need it. But by the way, no, I should say something. I think that this was the first proof. So I think they have obviously developed it more, and probably they have relaxed these conditions also more. So because this was in flat space, and now for example, this paper, generalizes the proof to globally hyperbolic spacetimes, which are in some sense closer to Minkowski, like they do deformation of Minkowski and study split property. So I don't know the current status of all the assumptions that have gone in. Yeah. No. That's a very good point. So I don't, to my knowledge, I mean this. No, I think this n is maybe in some special case. In general, no, it's not a constructive. As far as I understand, it's not a constructive proof. Yeah, but it does show us that we will localize information for sure. That it will show.
But some of this is stronger. I mean, I would have said that Einstein causality already tells you what we wanted to know.
No, but that's measurement. Now we are talking about preparation of states. We can Einstein causality tells us we can measure things simultaneously. But this is telling us because of the type 3 nature, we didn't know, because there was no factorized Hilbert space. So we didn't know whether I can prepare a state in O1 without affecting things in O3, right? No, that's not enough, because that just tells us we can measure the thing simultaneously, but doesn't tell us. The fact that it's type 3 is what tells us that my Hilbert space is not H located in O1 tensor, H located in O2, for example. There is no such split for a Hilbert space. So if I just look, the whole point is that if I look at the regular states, they are not split like this. So I have to look at some states which are generated by type 1, which will be like a bit sick from the perspective of von Neumann algebra. I mean, they are right. I mean, if this was all the type 3, I mean, okay, we can discuss a bit more. I mean, these things kind of go together. Like, you see, all sufficiently well-behaved states gave us this type 3 algebra. So you could have asked, how can we have, how could I ever get a type 1? And so that means that maybe I write, it will become clear that this the type 1 acts on some factorized Hilbert space, and those states are not sufficiently well behaved in this sense. But those are not important for us. I mean, they are just some auxiliary construction we use. But maybe Nima knows. I don't know if there is in general any explicit constructive result for this.
So what is the relation between the computation of operators and
Yeah.
the entanglement of states on which those operators act?
I mean, commutation just tells us that we can measure things simultaneously. I mean, there's no problem, right? If they're space-like separated. Entanglement was a property of Riesz-Leader. It came because of Riesz-Leader. So there are really 3 constructions, right? One was causality. One was the fact that we have relativistic covariance, so it gave us Riesz-Leader. And till we did Riesz-Leader, we did not state any type 3 or anything, because Riesz-Leader itself came just from even looking at the ordinary algebra of operators, right? Then we are now saying that, for various reasons, we looked at von Neumann algebra, and then we are really able to see that, which are bounded operators, and they are really able to see that we can't naively, if I just didn't have the split property, I wouldn't know how to prepare states in a lab without affecting state in a spatially separated region. Say that thing. The M01 are localized in O1, that's not a problem. But our omega is global, right? The whole point is that. And because M01 is type 3, so that is why M01 the algebra never factors into like a Hilbert space which is localized and something else. That doesn't happen. Yeah. Yeah. But that's where the intuition doesn't quite work. That's what I'm saying. That the intuition you have is that somehow MO1 when it acts, the state you will get. So you have omega. So you have a full Hilbert space H. The intuition, which is all our intuition, right, is that when some element of MO1 acted on it, it will give me some state, right? So let's take some psi. Psi is global, right? It's psi is not localized anywhere. A hat will act on it and it will give me some state. And your point is that this A hat psi will somehow be localized in O. No, A is self-adjoint. I mean, A's are
Yeah,
part of the
whoever's
one
speaking, can they use the mic, please? Because I can't hear anything on the Zoom. Some of the audience is speaking here.
Yeah.
Saying that you can choose A to be unitary when you're acting on O1. You don't have to make it non-unitary, right?
Yeah, it's just any generic element of bounded operators which is inside O1 localized.
And if I act with a unitary on O1, that will not affect the state on O2, right? Because unitaries will just cancel in the correlation function, right? So in some sense, you are changing the state on O1 without affecting O2.
No, but psi is not localized ever to begin with, right? Psi is not localized.
So can I also comment? Sorry, there's another question.
No.
But you can approximate it just because it's type 3, 1.
Yeah.
Yeah.
But I mean, of course.
That's different to what the split is doing.
Yeah. I mean, this is an exact statement, right? So that's where the issue lies. I mean, the whatever state you found, you could not think of that state as living in some Hilbert space which is localized inside O1 and the rest inside. Like you could not factorize it. That's the point. Yeah. Sorry, Suvrat wanted to say something.
No, I was just saying it's true, right? That if you wanted to physically prepare a split state, you'd kind of act with unitaries so as to kind of reduce the entanglement as much as possible.
Yeah.
And the small buffer region. So it's kind of right that, unitaries don't actually do this non-local thing. It's only
No. That is part of N. So I will come to that. So it is true that N is of course also bounded operators. And so when you act with these operators in N, they kind of give you some factorized state, right? But this N is N are not the our algebras of local quantum field theory. These are something that are a bit strange. I mean, they give a singular state somehow. Yeah. Yeah, that's a good point. I mean, I think some people, again, I mean, I should have disclaimer. I should again say a disclaimer. I'm not an expert in AKFT, so don't take my word for this. But I think some people do use N as if localized in a small strip outside O1. But at the level of rigor at which we are stating these results, no, we don't know if N is localized. We just know that N as an algebra contains MO1. Like that's what we know. I mean, I think that when you use it in practice, some people do attach N to like a region which is slightly larger. But I think I want to distinguish what are the results proved in AQFT from the sort of the practical applications. But so as far as I understand at this level, no, N is not. It is an algebraic statement, not a topological inclusion of O1 into anything. But again, I don't know if.
Maybe I can comment on this. So Roberto Longo and friends, they constructed the canonical split, which is a particular choice of split. It's explicit as much as modular theory is explicit. So you basically take one of the algebras and act with the modular conjugation of the both regions and add it to the original algebra to get type 1. And the result cannot be a algebra of a region because the algebra of a region is type 3, but the canonical split is type 1.
Oh, okay. Yeah. This is the standard split inclusion.
Standard split.
Yeah,
exactly.
Sorry, I forgot.
However, you could calculate that explicitly for the situations where one endpoint of the two regions is null separated, in which case you could actually construct. You can see that they become type 3-1 algebra of regions.
So like between O1 and O1 tilde, you are saying that. So
the split, standard split thing. The construction is general. When the two regions don't touch and they're space-like separated, then it's type 1. However, that thing exists even when they touch, and in that case, it's an algebra of a region. In some examples, then it's type 3.
Oh, I see. Even if these regions are like touching.
The construction exists, but the N is not type 1.
Okay. I see. And the explicit construction of the standard split inclusion is not just in CFT, right? It was in more general, for Longo et al.
It's just very abstract because it has a J of it. I mean, Tom has used this extensively.
Okay. Yeah, we have two experts who knows much more about this.
question related to previous question. So like, does it mean, does this display property mean given some space-time region, and I want to construct some QFT state out of the expectation value of observables, then I can approximate the states to very arbitrary small error using a type 1.
Exactly, I think that's the statement, but only type 1.
Okay,
yeah,
thank you.
Yeah, yeah. Okay, so I just give a quick outline of the I'll quantify split property a little bit because it gives us an answer about why information is localized in QFT. And then we can quickly switch to gravity. So this is a statement that so our algebras are split if we have a type 1 sandwich between A01 and A1 tilde. And what this means is exactly what we discussed earlier, that this implies that the existence of n is basically telling us that there's a unitary which takes us from H to some H1 tensor H2 such that action of n U inverse is actually equal to BH1 tensored 1, and because n contains A01, this obviously implies that U A01 U inverse is a subalgebra of BH1 tensored 1, and because O3 A03 is a subalgebra of a commutant, because O3 and O1 are causally disconnected, this clearly implies that the same unitary, if it acts on A03 or O2, sorry about that. U inverse is a subalgebra of identity tensored H2. So so this is the upshot of the split property. So it's very nice, right? We can do a unitary. There is a unitary transformation, and which is such that when you apply that unitary, which is what Suvrat was talking about, to kind of localize things, which basically will map any element of A01 as a bounded operator on H1. But these unitaries are not generated by the von Neumann algebras elements of the von Neumann algebra, because they of course depend on n, which is type 1. Okay, is there any question about this? Yeah.
Factorization of the Hilbert space is not necessarily associated to the same subregions, right? Because this n, as we were discussing earlier, we don't know if it's associated with a subregion itself. So can
we don't know. I mean, intuitively, I think as maybe Nima was also saying, maybe in the concrete examples, it would be this algebra will be localized inside a region including O1. I think that will probably be true. But the the way we have approached this problem, n is just some algebra which includes this. Now, if you look at the algebraic quantum field theory axioms, we intuitively feel that if n is associated to any region somehow, that region will include O1, right? But is that what? Sorry, maybe I didn't get your. Yeah.
So, but basically, there's no meaningful way in which you can say that H1 is associated to subregion O1.
Yeah, we know, but
it's just some factorization.
Maybe meaningfully we can say, I mean, roughly we can say that H1 is states which are localized like slightly outside in a region containing O1, but certainly excluding O3, O2. Okay, but I think that's probably a fair statement to say. Although I don't know if this proof reflects that. Is the Buchholz's original proof. Yeah. Oh no. It's just the fact that there is a type 1 von Neumann algebra n. The fact is type 1, and of course it's an algebra which is acting on H. H is our like Hilbert space that we have, right? Once and for all. Which came
H
from
is
omega.
fine. So
Yeah.
I understand there's an O1. Now, I also understand there's an N which contains that, which is type 1. Now, with respect to this O1 and N, what are H1 and H2 exactly?
Right. The fact that the fact that we are saying that N is a type 1 algebra acting on H implies that necessarily implies that there is a unitary basis change from H to a factorized Hilbert space such that N is identity on H2 and N is algebra of all bounded operators on H1.
Okay.
Yeah. Okay. So now let me just if there is no if there are no questions about this, I will just go to the localization statement of information in QFT. So now let's consider the following situation where we take two states. So let's first start with our omega. And then let's apply something from U or U. Let's say there are two elements A1 and A2 in U A1O U inverse, such that when A1 acts on omega, we got some psi 1, and when A2 acted on omega, we get psi 2. And now let's consider, let's say, the matrix element psi 1, psi I, O1 prime psi I, where A1 prime is in MO2. Okay, so that's the setup. But now you see that because A1 prime is unitarily related to a operator. Oh, I wrote it somewhere. Oops, did I delete? Oh, sorry. Let me just rewrite that statement again. Because this is true, you can immediately deduce from here that this, let me call this 1, equation 1. So you can deduce that 1 is so split property implies that psi I A1 prime psi I is equal to I mean, just a moment of meditation will tell you that if you just use split property, this is true because of the fact that psi i's were created in H1 entry, but A1 prime is acting only on H2, so it does not see the psi i's at all. So it's just an algebra, and you can just work it out. It's really not. I mean, it just follows from the split property and these unitary conjugations, and so this clearly implies that that MO2 cannot distinguish psi 1 and psi 2. So physically, let me intuitively say what this means, just completely intuitively. Basically, what we are saying is that somehow, you know, this was, let's say, your O, this was your O1, and you know, you somehow prepared a state here which was localized a little bit here, or maybe in some region slightly around it. So you prepared two states here, psi 1 and psi 2, and these states cannot be distinguished by some operator which was localized in a region here. So this one cannot distinguish between these two states, and so that's the statement of the, yeah, I just finished this. So localization of information in QFT. So it's in the way it's stated right now, it's quite an interesting diagnostic for gravity, as we will see, because at least the level of generality at which we have stated, it's true for all field theories in Minkowski spacetime. And if you believe that split properties exist for globally hyperbolic spacetime, then at this level of abstraction, it's true for QFTs without dynamical gravity. So so maybe I take questions now. So this is really the first main point, because we will see how this gets contrasted once we switch on gravity.
I have a question. I think it relates to what was asked previously.
Yeah.
So if this is like the main equation we are going after, this A1 prime.
Yeah.
Then acting with just a unitary operator inside of O1 will do the job for this equation, right?
Yeah. So that is what this. Yeah. No, I mean, this is a corollary of the split property. The point is that the reason I'm writing this is because this is what will become subtle in gravity.
Why did we need to go through the split property if this is the final object of interest? Because then psi1 could just be a unitary acting on omega, where the unitary is localized inside of O1.
But the unitary is not in the von Neumann algebra. So I'm saying that we started with a setup, right? Like, so if the unitary creates some singular state at the edge of the light cone.
No. Let's say it's bounded, unitary operator is bounded, and let's say it's completely localized within O1. It's just in the center of O1.
Yeah.
So then what is the...
But it can't be completely localized, because these functions are, I mean, you mean that, sorry, yeah, no, you're right. So,
but we can make a stronger statement, no, Alok, and then maybe this particular statement one can get.
No, but sorry, Raghu, I just want to, so this, I'm agreeing with you that we have roughly a unitary which is kind of almost localized inside O1, and we are creating a state.
Let's say there's a unitary which is completely localized within the open set O1.
Yeah, that will not factorize the state, right? I mean, that's the statement. Yeah.
Maybe, Alok, you need to insert like one more operator inside O1. So you want to say that there is no entanglement, right? You can find states which look like state psi1 inside O1 and look like state psi2 outside O1.
No, my psi1, psi2 are both are created by n. So they are intuitively inside O1, right? And I'm just trying to say that
this statement, then Raghu is right that this statement you could have got just by saying there are some unitaries that act that commute with that act entirely within O1. So for states which look entirely like the vacuum for something outside O1.
Yeah. This is one corollary. I agree. This is a corollary I could have stated, and in fact, in papers about localization, it is stated without going to the split property.
Maybe you can put another operator inside O1, no, for the statement. Like maybe if you put A1 prime and B inside O1, some element of the algebra inside O1, then you find that there'll be no entanglement. You'll get no cross terms.
But that is part of psi, no, Suvrat? So I thought it's just in the detail of psi, right?
Explicit, like if you put a B and then you put expectation of B inside psi. Like
right. That's what I thought. I mean, that's included in psi.
Okay,
I understand what you're saying. Thanks. So you are saying that you just put a B here, which is in O1, right? And then it factorizes. That's what you are saying?
Exactly. And the unitary won't be able to do that.
Yeah. Okay. Thank you.
Yeah. So, that is not, you can't achieve that so easily with a unitary.
For all B in M01.
Yeah, exactly.
Okay, thanks.
Is that okay? Thanks, Suvrat. Yeah. Actually, these states are, I think this, when you act with this, my understanding is that this, when you act with this U, maybe Tom can say it more, when you act with this U and the kind of states you get, they clearly don't satisfy the regularity property at the corners of O1. They do not satisfy. So they are not Hadamard. Like that's, I don't know, high energy, they are not Hadamard. They are like, they violate Hadamard.
So this is not understanding, Alok. Why don't you
the action of n operators on a state in H, they will not satisfy this regularity property at the end in the scaling limit, right? That's not obvious, I see. At least that was that is the one. Okay, maybe we can chat about this. Yeah, I mean, because it's not type 3, I thought the whole type 3 thing was that we have this regularity that we get right from the Hadamard in O1. No, that maybe no. Okay, but there must be something pathological that n does, right? Okay, I see.
It'll be somewhat singular, but if it's very far away.
Yeah.
Then it's not.
Absolutely no. Yeah, I was saying just that
in a limit, it will be bad.
Yeah, exactly. In the limit.
Sorry, Alok, I joined the stream a little late, so I'm a little confused about what you and Tom are saying. Why don't you just leave a small buffer region between O1 and something away?
No, that's the intuition of split property. That's the discussion. So n, if you want to think of n as the algebra localized somewhere, it's in a buffer region, including O1. But the split property statement is an algebraic statement.
Okay, but we can look at states which do satisfy the Hadamard condition, which are all finite energy states, which are in the Hilbert space, and still prove a split property, right? Because we can talk of a region, a buffer, and the complement.
Yes, I have not seen a proof of split property ever with the Suvrat, with the. I mean, at least I have not seen it. Maybe there is one.
Okay, I'm confused. Sorry, if you just all we are saying is we look at the algebra of three regions, right? O1 plus epsilon, and the complement of O1 plus epsilon.
Yes.
And then we write down the same statement that you had.
But M A O1 plus epsilon is type 3.
It's type 3, correct.
But that is not enough for split property.
I'll only prove the statement for when B is inside O1 and A is outside O1 plus epsilon. The statement you have on the board. You're saying we can't do.
But okay, maybe it's in some approximate sense, but the split property is really a statement that we need a unitary which will split our Hilbert space in two, no? H1 and H2, which requires a type 1. I mean, is that Tom? Is that correct? Or I think split property cannot be stated without the type 1 being between them, right?
Yeah, that's fine.
Yeah.
But those operators, they don't have to be singular.
No, that's fine. No, I was saying that the action on the state may do something in the short distance limit, which is not what.
Yeah.
That's all. Yeah, I can hear. Oh, I see.
So this equality, so if the state is not completely factorized, but only approximately factorized with finite energy, then this equality with A1 prime B, is it exact or is it approximate?
Yeah, no. The split property is, our demand from split property is exact separation. Demand is exact separation.
No, the separation is exact, but in this equality of correlators.
Yeah.
So that is like saying if I take a 2-point function with one operator in O1 and one operator in O2, just the Whiteman function is 0. Right? If the 1-point function was 0, then that seems very unnatural. If it's a regular state, because there will always be some space-like correlation.
But that's what I'm saying. That's why regularity somewhere gets compromised by these operators in the state.
Sorry, this is not true physically, right? Physically, if you leave a buffer region, this is how Haag states it in his book. Then the state is completely regular and you can have 0 Whiteman function. Like nothing stops you if you. It's what maybe Sandip was saying. If you have lattice separation, so I leave a few lattice sites in the middle, and I restrict O entirely to O1 and leave something, then I will get 0 Whiteman function.
But Suvrat, I mean, the split property itself is an inclusion of type inside type 1 is required, right? Because otherwise we don't have a factorized Hilbert space at all.
Yeah, sorry, this might be a little too formal for my
okay, but but
the correlation statement of the kind Raghu is asking about, and I want to say there's 0 Whiteman function between a ball and something outside, provided I leave a buffer in the middle about which I say nothing. Like the ball is.
You're saying just having 0 Whiteman function is completely okay, and that's fine.
Fine, yeah. Because the points are never going to come too close because of the buffer. It's always Whiteman function at finite separation is going to be 0.
Okay, that's fine. Yeah.
Okay. So I did start gravity. Maybe if there is no more questions, then. But you have more questions, direct them to Nima or Tom, by the way, because they are the experts. Okay. So now let me. I don't have much time, so let me start. Maybe I can take 2 minutes because I stopped Tom, right? So I feel guilty extending my time. So I'm just giving a brief outline of what we will do in the last lecture on Saturday. Okay, so the fact that there is some localization of information in Q of t, we want to ask, to what extent this thing will be true in gravity. But then the first question we want to ask is, what is the algebra of observables that we start with, even the abstract algebra? And this is where already, so one approach, of course, which is not the only approach, is to start with classical observables. So one approach is to start with classical observables in gravity. But I should mention that within algebraic quantum field theory, there is a completely different approach they have taken, which is way above my pay grade, which goes under the name of locally covariant quantum field theories, which are some field theories defined on some category of manifolds, category where objects are manifolds, and then you have diffeomorphisms between them, which don't start with any classical observables. But I haven't understood their construction, so I will not talk about this. So at least the more down-to-earth approach is to, if we could understand algebra of observables in classical gravity, then we could try to follow this approach we had, where we start with this abstract algebra and try to localize them, like at least in perturbation theory. So that's what we want to do. So let me just give you a brief. Already here things become quite rich as opposed to ordinary gauge theory, like abelian gauge theory, for example. So I will just classify the kind of observables we find. So this is just a cartoon. We will be more precise in the final. So we can deal with two cases, and then one class of observables which are gauge invariant or diffeomorphism invariants are what are called boundary observables. And so, for example, in asymptotically ADS spacetimes, these are really, one way to define them is take a Cauchy slice on the boundary and then look at all the stress tensor in the Pfeffer-1 Graham gauge localized on the boundary. So we can ask, okay, what is the algebra of operators generated by these boundary stress tensors? Of course, smeared with some smooth function on the boundary. And if we could find an algebra of this type, maybe that is one possible algebra of gauge invariant observables. As we will discuss, that it's hard to actually know what this algebra is, because it's hard to find the commutators between these T's unless you contract them with isometries of the boundary metric we will discuss. So we don't really know this algebra, but we know it exists, but it's an abstract algebra. I mean, but in the flat case things are a bit better, because as we will discuss, there is algebra of boundary operators in semi-classical gravity, and that algebra is generated by what are called News operators. And that algebra is actually algebra of free field operators, free field graviton operators. So unlike in ADS, things die down, and then you get a nice analytic algebra of boundary operators. So already at this level, we start seeing a difference between some technical difference between structure of boundary observables. But of course, boundary observables cannot help us. If there was nothing more than boundary observables, if you could show there are no other observables in gravity, then there will be no localization of information, because then the states we are creating are always going to be delocalized. But but that's not true, at least in classical gravity. And there are a class of observables which are called relational observables. And this class of observables have a long history, starting from Bergman and Komar's work in 50s. And especially I strongly recommend a paper by Philippe and his collaborators that came out, I think maybe last year, where various notions of these observables are explained in a beautiful manner. So this, I don't remember the number, I will give you next time, but I would say it's the most state-of-the-art discussion of relational observables right now. So these are observables which you define kind of locally, like they can be defined locally because they are relations, and they satisfy classically, as we will discuss next time, our principle of microcausality, classically. So then we could hope that at least in perturbation theory, if we start with this algebra, and then you do the same thing we did with the algebra of quantum field theory in the scale, let's say scalar field case, maybe we could also have a notion of split property. But okay, I will try to argue that even in that case, we won't find split property in when gravity becomes dynamical. So okay, so I went over time. I'll discuss this next time.
Any one quick question, because there are already a lot of questions.
Yeah, at this point, I will first define them classically. Yeah, because of course, once quantum gravity is not renormalizable, so any composite operator becomes too complicated to deal with. But that we will discuss them.
So I just have a comment. It's more like I guess asking if someone in the audience knows about this. So I've never understood this argument of Fermi and this paradox of Fermi and its resolution by Buchholz and friends. But I think potentially a closely related topic that's familiar to our community is this example that Pesky and Schroeder discussed in section 2 or 1, which is if you take the propagator for relativistic single particle quantum mechanics, you will see that outside of the light cone, there's always some propagation.
Yes, of course.
And this is intimately related to this paradox, this seeming paradox, when you model the two atoms and a photon propagating in between them. Now, I've never managed to fill in between, but I think that's perhaps the simplest context.
Okay, thank you. Yeah,
high energy theorists can understand.
So Matt is saying it's called the Klein paradox.
If there are no more questions, let's thank Alok again.
Thank you.